We will build upon the work of section 10.4 and derive the regular polygon area formula, or at least one form of that formula. So a bit of review work before we do that, because what we do here will be based upon that previous section and the results that were proven there. So we proved that inside every regular polygon, a point exists that is equidistant from the vertices. We called it the center, and we said that a segment from a center to a vertex is a circumradius. And once that section was done, perhaps that term circumradius took on a new significance, because it is the center of a circle circumscribed about the regular polygon. We noted that that result followed, that the circle exists. So here's a picture to illustrate the idea. So we have in this diagram a regular hexagon. The center point exists. There it is, point C. And we constructed in all the segments from center to a vertex, all the circumradii, and these are equal in length just by definition. We also discussed apothegm. An apothegm is a segment that goes from the center out to a side perpendicular to it. And we know that all the apothegms are equal in length. Here, let me pop over to that. All the apothegms are equal in length. And that each apothegm bisects a side, which means that all the half sides are equal to one another because the sides to begin with were equal. And then pop back for a second to review a result that we proved about the circumradii. Each bisects an angle. So these two results about circumradii and about apothegms, that is, that circumradii bisect angles and that apothegms are equal in length and bisect sides, we will make use of these to now derive the regular polygon area formula. So we'll need some variables here. So let n represent the number of sides. And yes, I know that in the picture that's 6, but the work that I'm about to do will apply to any regular polygon at all. I just simply needed a picture. And in that picture, we have to have some number of sides, so 6 it is, but I will not assume that the number of sides is 6. Instead, I will use the variable n. Let us say as well that a length of an apothegm is a, and those are all the same as we know. And let's say the length of a side is s, okay? Now, let's derive an area formula for this regular polygon. Okay. Now, if I were to just give you a regular polygon, if I were to say something like, here's a regular hexagon of side length 12, find its area, I don't doubt that at this point in the class you would be able to do that. I mean, it might take you a few minutes to hit upon a technique that would deliver the area, but you could definitely do it. And I suspect that what you would do is this, is you would create a triangle that consists of a circumradius, I think this is unavoidable to do this, an apothegm, we had some of this already, and then a half side. This is like the crucial triangle. We can work with this. We know about this, okay? So let's think for just a moment about how it is that we could, first of all, get the area of this triangle, and how it is that we could turn the area of that triangle into the area of the regular polygon. Well, as for the area of this triangle, it's a right triangle, and usually the easiest way to find the area of a right triangle is to simply take half the product of its two legs. I mean, we know the area formula for a triangle is half base times height, but if you choose as your base one of the two legs in a right triangle, the height is the other leg. So let's go ahead and write this down. So the area of one of these triangles, and you could create many of them, the area of one of these triangles, make this a bit neater, the area of one of these triangles is, there's your general purpose triangle area formula, which is half base times height. And what that becomes in this case is half of, let's say the apothegm is our base, and then, as for the height, that's the other leg, and remember that each apothegm cuts a side in half, so that would be times s over 2, or I'll simply call this as over 4. Okay. Now, we could, of course, create multiple of these triangles, and thereby completely exhaust the interior of this regular polygon. And as a matter of fact, we would have two triangles just like this for each side. So here would be the second for the side on the bottom. Here would be one for a side on the left, and here would be another for the side on the left, and so on. And we can continue all the way around. And it's trivial at this point, given what we know about apothegms and circumradii and so on, that all of these are congruent to one another, which means their areas are equal. So to get the area of the regular polygon, which I'll call it RP, we would, of course, have to multiply the area of a triangle by how many of the triangles there are. And there are 2 per side. And the number of sides is n, so there are 2n of these. So the area of the regular polygon is 2n times as over 4, which I'm going to write this as, rearrange this a little bit, as 1/2 NSA. And sometimes that's the form that's given for the area of a regular polygon, and that's just fine. That's half of the number of sides times the side length times the length of the apothem. But there is a nice way to compress this, a way that will be particularly helpful to us when we come to discuss circle area. For consider n times s. N is the number of sides, s is a side length, which means then that n times s does represent the perimeter, which I will designate with the capital name of a capital P. So what we end up with then is half perimeter times apothem, and that is my preferred form for the area of a regular polygon. So how will we apply this? Well, typically the problem will be this, is you'll be given a regular polygon, okay? Sometimes a picture, maybe just like the number of sides is 12 or whatever, and then you'll be given some value, and that will either be a side length, an apothem length, or a circumradius length, okay? And then you will be asked to prove you will be asked to find the area of that particular regular polygon, okay? Oh, and I've done something here at the bottom that I just noticed. I gave the half NSA formula, so instead, let us say that we'll use the half PA formula. Though if you like the half NSA, use the half NSA. It's equivalent to the half PA, of course. So what do you do then with your regular polygon and your bit of information, given information? You mark the center. You drop an apothem from the center. From the center, you also draw out a circumradius so that you end up with the right triangle. And then you reason about that right triangle, which will always involve the determination of an angle measure. So let's actually look at a particular example. So we can begin to get a sense of how it is that we could go through this process and find the needed angle measure. So here we go. Mark the center point, drop an apothem from that center point. Also from that center point, drop in a circumradius so that you end up with the right triangle. We are told that the apothem is 12, though sometimes you'll be given a side length and sometimes you'll be given a circumradius length. In this case, the apothem is 12. And then we plug into 1/2 PA. Well, A we got, A is 12, so the whole task really is to get the P. So how are we going to get the P? Well, we're going to start out by getting a side length over 2, which is the portion, the piece of a side in this right triangle that we created. And then how are we going to get that? Well, here's the point where we have to begin to think about angle measures, okay? And there are 2 ways to go about this, one of which I think is easier than the other. You could either find the angle that I've called alpha in the diagram, the one up there next to the center point, or you could find the beta, the one that's next to the side. I think alpha is easier. How would you find alpha? Well, remember that this triangle that we created, we can create 2 just like it for every side. That means that we have 2n of alpha, okay? In this case, n is 6, so we would have, if we created all the right triangles like the one you see, the one I created, you would have 12 of alpha. So the measure of alpha would have to be 360 divided by 12, because of course, as we go once all the way around that center point and create all those right triangles, the sum of that sweeps out 360 degrees, and then divided by 12 would be something that would be actually 30 degrees. So that alpha is 30 degrees. And that's fairly simple. You could also find beta if you want, first directly. And the way you do that is this. You recall that each circumradius bisects an angle. So beta is half an angle measure inside the regular polygon. And how do you find an angle measure in a regular polygon? Well, the number of sides minus 2. This is the formula that we derived a few chapters back. So number of sides minus 2, in this case 6 minus 2, times 180 degrees, divided by the number of sides, and then beta is half of that, which of course then will have to turn out to be 60 degrees. Do whichever you want, but I think the first of those to find alpha is easier. Okay, so once we know the angle measure, we can find the side length over 2. In this case, we have a 30, 60, 90. Do not assume that no matter the regular polygon that you have, no matter its number of sides, that you'll always get a 30, 60, 90 when you create this crucial right triangle. You won't, okay? You'll get a 30, 60, 90 for a hexagon. You'll also get a 30, 60, 90 for a triangle, but with the 30 and 60, their positions reversed. But otherwise, you won't. If it's a square, for instance, it'll be a 45, 45, 90. If it is a regular pentagon, then I believe it'll be a 54, 36, 90, if my math is correct. You're just going to have to find out what the angle measure is, okay? Now, in this case, with the 30, 60, 90, we can get an exact expression for the parameter, and here's how we do that. And I'll come back and talk a little bit about what you would do if you can't get an exact value. So let's see, the side opposite 60 degrees is the 12. So the side opposite 30 degrees is, do a little side work off here. The side opposite 30 degrees is the side opposite 60 divided by root 3. That's the basic relationship in a 30, 60, 90. The side opposite 30 is the side opposite 60 divided by root 3. And it will certainly be in our interest to rationalize at this point. So that becomes 12 root 3 over 3, which is 4 root 3. And that's what s over 2 is. So s itself, of course, is double 4 root 3, which is 8 root 3. And then as for the total perimeter, I'll pop back over here and get that. Well, that's just simply the number of sides times the side length. In this case, that's 6. And then times 8 root 3. So that's 48 root 3. And then at that point, we can plug into the 1/2 PA formula. So that's 1/2 times 48 root 3 times, sorry, it's a bit messy, 48 root 3 times 12. And I'm not going to go through and simplify that down, but that's how it is that you do that. Now, final question. What would you do if your polygon was not nice like the hexagon and you didn't end up with a 30, 60, 90, or like in the case of the square, 45, 45, 90? Well, you do the work to get the angle measure, and if it turned out it was like 54 and 36, say, you have no choice at that point but to do trig. Trig is the tool for you, which means, of course, that you will get an approximate answer at the end, not an exact one like in this case. But the technique is the same, except, of course, for that little twist where you have to do some trig. I'm not going to actually do this one all the way out, but just to show you how the trig would be involved. So this is a regular pentagon. Okay, so there it is, circumradius and apothon. We create our right triangle. So R is 1, where R represents the circumradius. And then we're going to do the 1/2 PA, but like I said, we're not going to carry this all the way out. Let me just give you a sense of how this would be done. So let's see, I'm going to do the alpha up there. Okay, so how many angles do we have like the alpha? Well, we got 2 per side, 5 total sides, so we got 10 like that. So that's 360 divided by 10, which is 36 degrees. And then with that, I can get A and S over 2. And you're going to do trig, right? So cosine, which is adjacent over hypotenuse, so cosine of 36 will be A over 1, and that allows me to get the value for A. And then the sine of 36 degrees would be S over 2, which allows me to get, S over 2 over 1, which of course is just S over 2. And that allows me to get the value for S. I do assume here that you remember basic trigonometry. And once you have A and S, it's an easy matter to get the value of 1/2 PA. So I'm sure you can do that. Oh, final little thing here. If you look in the answer key, you will not find answers for this particular set of problems, and you might wonder about why that is the case. Am I lazy? Well, yeah, it's as lazy as I can get away with, but I didn't need to do it in this case because you've got Wolfram Alpha. Go over to Wolfram Alpha and simply type in a description of your regular polygon. It's smart. It will recognize it. So if you were to say, like, area regular sixagon, apothon 12, literally, if you were to type that into the Wolfram Alpha search bar, it would tell you the answer, and it would tell you probably more than you want to know about this, but it would give you the exact result, and it would give you an approximation as well. Or you could do something like area regular 9gon. Yes, Wolfram Alpha knows what a 9gon is, and you could say circumradius 3, and it would tell you the answer. So yeah, hop over to Wolfram Alpha and find out what the answers are.